Today I'm going to implement debug information in the PDB generation of my linker. So the way this is supposed to work is that while compiling, the compiler emits two special sections, the debug S section and the debug T section. The debug S section being for symbol information and the debug T section being for type information. So today we are going to care about the type information, and while this debug T section contains actually type and ID information, we will see a little bit later what that means. But how this section works is that it contains some sort of signature, 4-byte signature being CV signature C13, which is just 4. And then there's just a sequence of type and ID records. So here previously in the file I kind of talked about how these type and symbol records and so on work. But essentially, maybe here's a good example. So this is how they look in a dumped format. So this was dumped by CV dump. And so how they work is just there's some type indices, then there's a leaf, which tells you what kind of type record this is. In this case, this is an LF arg list. So the type is like the argument list of a function. And it just says, well, the first member is nothing. So this would be equivalent to void, kind of in an int main void kind of situation. And then there's a procedure which returns an int, which kind of is the same as in the example right there. And this would be the type of a procedure, for example, and so on and so forth. And importantly, each of these sort of is implicitly allocated with a type index, which starts out at OX1000, the first 1000 being reserved for basic types. For example, this int 4 is type index 47, which is less than OX1000. And then future types can reference prior types through this type record, through this type index. So for example, this LF procedure has the arglist type of OX1000, which is this type right here, which is an arglist. Okay. So now we have these. These are for every object file. Every object file contains a list like this. Now we have to create one list containing all the type records for all the different object files. So more or less we have to implement some sort of merging of all of these type records. And where do they get merged to? Well, if you have seen previous videos on this PDB stuff, there are sort of some streams. Each of these streams has some sort of layout, and we merge all of these type records into the TPI stream or type information stream. And then there are also these ID records, which I've mentioned, and these go into the IPI stream. Okay. So the plan for today is to write out a TPI stream and an IPI stream, which contain the merged symbol information for all of the different types and IDs contained in the program. Okay, so I currently don't have much. In particular, this writePDB function does not take any arguments, but now we have to change that. Now it takes as an argument at least all of the type information structures of, well, the different object files. So let's see where writePDB is called. It's right here. So here, where we are in the main procedure of the linker, we have to collect all of these debug T sections. So what I'm just going to do, I think it's called object files right here. Just going to iterate all of the object files. For u32 object file index smaller than starts out at 0, object file index smaller than the amount of object files. Object file index plus plus. We are taking the object file at object file index and put that into object file. And then each of these object files, if I look at it, contains section headers. So next step is we're going to iterate all of the section headers. I think. Okay. So for with the section index starting out at 0, section index smaller than object file amount of sections. Was it called that? Number of sections. Section index plus plus. Get out the section header. Headers. Now, the conf section header doesn't actually give us the data right away, but we have to get it from the object file. So what it does give us is pointer to raw data and size of raw data. Let's grab these out. Size of raw data is just section headers. And there. So this size of raw data and the pointer to raw data. And actually, I only care about the section header if it is the debug T section. So if string comp, I guess, of the section header name is .debug $s for at most 8 bytes. Then I want to fill in this data right here. So we have the size of raw data and the pointer to raw data. And now we can use some of those stream routines. So stream read array by pointer, maybe. No, stream read range by pointer is the one I want, which takes the start and the size and the count, which the size is just going to be 1 because I'm going to assume it's plain bytes. And then the stream is in the object file. So object file stream. The start is the pointer to raw data. The size is the size of raw data, or the count is the size of raw data, and the size is 1. And I'm just going to say U8 debug data is this. Now I think I've checked that all of these are in range, but let's check. That would be in parse object file. Here Section data. Stream read range by pointer. Yes, so pointer to raw data, size of raw data. I did exactly this once before when I passed the object file. So I'm sure that this debug data is fine and that isn't outside of the executable. And so I want to now create a stream for this data. So struct stream debug s, let's call it, is just the data is debug data, and the size is size of raw data. And the offset can be 0. Now we have this debug s data, and for each of the sections, if we have them, and we want to specify this to the writePDB function. And so for writePDB, I'm just going to define an argument. So let's call it struct writePDB information or something. And this is then going to take the amount of object files it's going to take a debug s stream pointer for amount of object files. So maybe this debug s streams. Wait. We said we cared about debug t. Sorry. Debug s is going to be another time. Okay. Let's maybe call this type information per object. Okay. Then I am going to allocate one of these on the stack. writePDB information. Starts out at being 0, I guess. And then right here, we can fill in all of the information. So the amount of object files is the amount of object files. And what else did we care about? The type information per object. So let's allocate a stream for each object file. I think we have an arena here. Yeah, we allocate it right here. 64 gigabytes. Okay. I hope I don't need that much. Anyway, push array into the arena of streams. For how many we care about amount of object files. And so then we can fill in this type information per object right here. So instead of naming this debug t, I'm just going to say type information per object of object file index is stream of the data being debug data and the size being size of raw data. Okay, so far so good. Let's see that builds. Yes, and it just tells me this writePDB information is not used. Which is fine because we are going to use it right now. So we have the PDB information stream, we have the name stream, and now right here I am going to start struct memory arena for the TPI stream and the IPI stream, and I'm going to fill these in at the same time, I'm pretty sure, the way I thought about it, but we'll see. These do have the same layout, so if I go into the information, because we have to fill them out anyway now, so in the documentation where I talk about these two streams, this is too far already, the EBI stream is too far, but it should be right here. Yeah, the TPI stream contains type information for all types used in the executable. It's always present and located at fixed stream index 2. And it starts with the following header. So let's maybe declare this header. And say struct TPI stream header. TPI header is push struct, so allocated in the TPI stream and the IPI stream. Push struct into the TPI stream. We put one of these. And then we copy the line and say TPI, IPI. Then we have to fix up the types. Okay. And then I also want to write both of these streams. So going to the top, you have them at 2 and 4. So I can do the following here. The streams of TPI.data is the TPI stream base, and then the size is where we currently are minus TPI stream minus the base. And the same we do for IPI. Okay, so far so good. Complaints about this not being used and these two not being used, but that's fine. Now, how do I start this? I think I want to fill these headers in the very end. And just, for now, try to more or less dump all of the type information. So we can kind of see how this would work. And so I talk about this here. So in this way, each type record is assigned a type index. Yeah, I talked about that a bit, which the CodeView format uses to reference types. Each type record starts out with a header. And here, so it has a header which has a length and a kind, and the length field itself is not included in the length. And so you iterate by casting the thing to the header, and then in the end adding to the offset the header length plus the size of a U16. And I made all of these streams, all of these debug T section streams. So we can use the stream abstraction that I usually use in this, at least. I'm trying it out in this to iterate the debug section, so the loop will look a little bit different than it does here, but that will be fine. So let's iterate all of the object files. So for U32 object file index 0, object file index smaller than the write PDB information, amount of object files. Object file index plus plus. So just iterating all of these. And then in the PDB write information, how did I call it? Write PDB information. We have the type information per object. So write PDB information, type information per object of the object file index. Now we want a loop that kind of looks like this, but I'm not going to use offsets. Maybe I'm sort of going to use an offset. Maybe the stream has an offset and a size. So I'm going to say while type information dot offset smaller than type information size. And while this is the case, we first read the header, I think is what I'm going to do. So let's copy this. Type record header. And maybe then I can put the while loop here and say while the stream read of the type information stream for the type record header and the size of the type record header does not fail, and not failing means it returns 0, which means we have to negate this. So while this is unequal to 1, so 0. Okay. And then in the end we have to let's calculate the record size, I think. Which is the type record header. Because the length includes the kind value, we have to subtract size of type record header dot kind. Well, if this is negative, I don't know what to do, so. We are just going to say it's corrupt, which maybe means sure, let's just break for now. That's fine. And then in the end, we have to skip the record size. And the way I'm just going to do that is I'm going to use stream read by pointer of the stream, which is the type information, for the member size, which is 1, and the count is the record size. So we have record bytes, record data, let's say. And if we cannot get the record data, we also break. Okay, very nice. And now this loop should kind of implement exactly this loop right here, which just iterates over all of the different type records in the stream. This also starts at a type index of the minimal type index, which for us will always be implicitly OX1000. So let's keep that here. Type index, because the object files do not have a explicit type index space like the PDB does for whatever reason. So the type index space is implicit OX1000. And yeah, then let's copy this printf to dump all of the different type indices. So the type index plus plus, which we are going to fix afterwards, that happens somewhere else. And then the type record header length and kind. Then I'm also going to put a bunch of new lines every time we start a new object file. Let's say in between the new lines, new object. Maybe like this. Okay. Error. Type record header length. Printf undeclared. Print is declared. Now to test, for now I'm going to use the simpler test. Later on we can go back to the broke CE game to test that it really works. But for now I use this test.bat, I think. Right here, which just links compilation unit 1 and compilation unit 2. And so these, if you haven't seen them before, test some very basic stuff about linkers. Okay, so we're going to use that, and that is supposed to produce a.pdb right, test.bat. And this was supposed to print the bunch. Well, I guess these are not compiled to contain debug information. Maybe it. Actually, I'm missing one thing. Okay. Because I said in the very beginning, before I forget this, that these debug S and debug T section both start with a signature. Blah, 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 blah. Object files. Both of these sections start with a CodeView signature, a 4-byte value of CV signature C13. So here I'm just going to say if the type information U32 signature, let's say, if we can, if the stream read fails on the type information for signature size of signature, which might happen if either there's a very small debug T section or if there isn't a debug T section, in which case this type information per object will just be empty. So if this happens, or the signature is not a CV signature C13 or 4, let's copy this value and put it as a comment right here. In that case, we just continue and process the next file. Okay. So far so good. I wanted to make sure these compilation units in test.bat are compiled to contain debug information, which they are supposedly are. Okay. So let's see, dump bin compilation unit 1 dot obj has a debug S and debug T section. Then let's see where we are trying to get these out in linker at the very end. I don't fill in the streams, but I do it here, but I don't set the value. So the type information per object is the type information per object. Who would have guessed? So what was probably happening there was that it was crashing. That's why it took a little bit longer than I expected. Test that. Yeah, very nice. There are 2 objects which apparently don't contain anything according to this. I guess let's see if that's true. With using cvdump. cvdump compilation unit 1 dot obj. No, there's supposed to be some stuff in here. So these are the types, as you can see, and the first thing is an elif arc list. So why are we not printing anything? In write PDB. So let's just dump a bunch of these values and see what they give us. So let's print the type information. Let's print the signature. And then at each step, print the type record header. And yeah, maybe that's fine. Test.bat. So we can see there are some The type information looks decent. It has a size, it has an offset. We get a type record header. With a kind and a length. Looks decent to me. So we calculate the record size. And that's smaller than 0, we break. Otherwise, we do read array by pointer for the length. Print the record size. After we calculate it, and then let's print the record data. Record size is 8. Record data is something. I did the thing again. I don't know why I do that this often. If we don't have record data, we break. Not if we do have record data, we break. Okay. Remove all the print stuff and rerun it. Okay. And there's one more print. Okay. But these look fine. We can see they have type indices. They have a length that is quite small each time. And they have some sort of type. Now, I think next I want to collect all the types that I actually need. So all of these kinds. The way I'm just going to do this is have an array right here. So kinds we need, which is maybe 100. We definitely don't need that many. Then we have a U32 kinds we need at, starts out at 0. Every time we end this loop, right here, I'm going to iterate for 32 kind index 0, kind index smaller kinds we need at. So just iterating all of the ones that we already have. Going to check if the kinds we need at the kind index is type record header kind. If so, we just break. We set maybe int found 0. And if we couldn't find it, we set found. If we found it, we set found equals 1. And in the end, if we couldn't find it, we say kinds we need at kinds we need at plus plus is the kind, type record header kind. Okay. And if we have those, which the declarations are right here, so here I can just print all of them. Okay. So for these two executables, we need these kinds, which is fairly small, which is fairly nice. But it makes sense because these two executables right here, so compilation unit 1, compilation unit 2, don't actually use that many types. It's pretty much just function types. So this function type right here, which is this function type, and this function type right here. But that's probably enough to get started, and then later on when we attempt to compile or link the bigger broke CE game or something, then we just have to implement more of these different records. But anyway, we have this list. So let's here switch on the list of type record kinds. Case. And let's sort of order them by the value, I think. So these are the ones we have. Now, each of these type record kinds corresponds to one of these LF pointers, LF function, LF procedure, or whatever it was. And we find these by looking into the how do I not have internet? Yeah, be right back. Okay, I'm back. So we find these in the cvinfo.h file in the Microsoft PDB repository. And so essentially there's a giant list of them. Here you can also see the CV signatures C13, but that's beside the point. And yeah, this whole file is a giant array of stuff telling you what type indices are and so on. And so we care about these numbers. So what is OX 1008? LF procedure. What is OX 1201? LF arglist. Makes sense so far. And then these other ones actually maybe sort of more interesting for us, because all of these in the 160XX range, which are not that many as you can see here, are actually these ID records and not type records. So they will go into the IPI stream and not the TPI stream. So this is LF func ID, LFM func ID, which is a member function, which we thankfully don't have to care about for C. Build info, and then string lists to make up the build info. UDT source line and UDT mod source line. Okay. So this is a 1601 is a LF func ID. Let's order these correctly. Then OX 1603 is a build info. And then we have substring list. And we have string ID. And so here ID records. And so these go into the IPI stream and not the TPI stream. Now here comes the thing I talked about, where we do need to care about, so we have all of these different type records from all of the different object files, in this case only 2 of them, but they share the same type indices and they use the type indices to reference other types. Like a pointer type references what it is typing to, what it is pointing to using the type index. Which means here we have to remap all of the type indices from these local type indices, I guess, to the global type indices that we calculate in the PDB, in the IPI, TPI section. And so let's remove all of this gunk. We need to map where do I put this? Need to remap all of the type indices used by the type records. From the object file local ones to the PDB ones, I guess. And so there are 2 parts to this. One part is just to remap the type indices by doing exactly the switch statement, then understanding all of the records and remapping the type indices. And the second part is that you don't want to emit the same type record multiple times. And so you have to hash the type record and to deduplicate it. For now, let's not do the deduplication, just emit the type records after we've emit the, let's just emit the type records after we have remapped the indices. But we still need to know the indices in the object files, what they map to, where we emitted them. And so I need some sort of map. So let's say U32 object file index to PDB file index map. Beautiful. And so we have this map and we need to do 2 things at the same time. We have to emit this map. Okay. My brain is going all over the place right now. So linearly, while we are emitting these type records, we then know where the associated type record is in the PDB file, which means that we can linearly, whenever we push one of these type records, we then know where the next entry of the object file type in the object file, there's a type missing. Object file type index to PDB file type index map, where the next entry in this map is. At the same time, we don't want to allow you to go out of bounds, so we have to bounds check that in both directions. because also the lowest OX1000 type records are, well, these basic types, and so we don't want to remap those. So first of all, let's say we daisy chain this map. We daisy chain this map into arena, let's say, because I think we have that. Whenever we emit a type, or whenever, yeah, we handle a type record below. And let's verify that we have an arena, but I think we do, yeah. And here we say push the type record to the stream and insert an element into the type map, I guess, into the object file type index to PDB file index, whatever map, into the map, let's just say. And so if it's one of these ID records, type record header kind is between OX1600, which would be, well, yeah, that's something here. And I don't know if I should say equal or not. Let's say equal. And the kind is also smaller than OX1700. This is an ID record and needs to go into the IPI stream. So else, let's copy this. This is a type record. Needs to go into the TPI stream. And that PDB type index is set based on which one this is. And here it is IPI or IPI type index at, here it is TPI type index at. And finally, we can push an element into the map. Where is it? Here. push array into arena of U32s, but 0 of them. Okay. So far, so good. Now, this is an ID record and needs to go in the IPI stream. This is a type record and needs to go into the TPI stream. The way we emit one of these type records is first we have to emit a CodeView type record header. So struct, and there we can just copy the header. So push struct into the IPI stream in this case. And the value is just the header. And then after we've fixed up the record data, we can then also copy the record data. So push array into the IPI stream U8s for record size, and to be memcopy in the record data for record size. Here we do the same thing, but instead of IPI, it's TPI. Okay. Now, we need to remap all of these indices. Let's do that right now. So of procedure. of procedure looks like this. So this one we've already have. Oh no, wait, that's the 16T one. We care about this guy. This we've already skipped, and then there's the return value. So struct U32 return value, and that's a type index we have to fix up. There is an U8, which is the call type. There's another U8, which is the function attributes. And there's a U16, which is parameter count. And then there is a U32 arc list. Let's call it procedure. And this we just cast as void star from the records data. Now to make sure this fits, I'm going to say if the size of the procedure is bigger than the record size, we break. Otherwise, we need to fix up the procedure return value and the procedure arc list. So a procedure return value. And so here we need to do the remapping. And the remapping, sort of, what we want to do is we want to take this map and we want to just put in the procedure return value. Obviously, this doesn't work for a couple of reasons. First of all, this starts at 0, but the type index starts at 0x1000. Second of all, this is not bounce checked, which is it needs to be. And third of all, the smallest 0x1000 should get mapped linearly. So I think I might make like a remap macro really quick. So define remap type index, let's say, and we take a, well, like value, let's call it v. We say v is equal to v is smaller, let's use some parens, v is smaller than 0x1000, then we are going to use v, else if v is bigger than the bigger or equal to the type record we are currently at, then we say just 0. This is like an invalid PDB, pretty much. You're not supposed to have a type. Something is not supposed to refer to something that comes after it. And otherwise, we can just use this map of the type of v, but we have to subtract 0x1000. Okay. And so here I can just say remap this value, or remap type index. And we also want to remap the arc list. Okay, beautiful. Next one. The arc list. The arc list has a count for number of arguments and then a type index for each argument. If size of U32 for the count is bigger than record size, then break. Else we get out the count. Then we check that we can fit all the type indices. Minus size of U32 is smaller. Let's use the same way around so we don't get confused. If count times size of U32 is bigger than the record size minus the size of U32. Here we sort of have to care about overflow, so let's cast this to U64 each side. And the record size is at least 4, so this should be always positive. Okay. For U32 argument index is 0, argument index smaller than, let's call it argument count. Let's just take it count. It's fine. Argument index plus. We want to remap type index of okay, let's actually make a structure for this to make it a little bit cleaner. So struct u32 count, u32 argument type is a trailing array member, arg list, let's say, void star record data, and we can do the same. So size of, this is way better. Arg list is bigger than record size, we break. Otherwise, we don't need this count. We can use the arg list count. Yeah. This works. And then we can remap type index of arg list argument type of argument index. Beautiful. Then lf func id. Has a item ID and a type ID. But the way the loop works and this remapping works, I don't think that makes a difference, because this is sort of what this part does. That still the type ID should be correctly in the map, and the type ID should be correctly in the map. Okay. So structs func ID is void star record data. We don't care about this trailing data because it doesn't contain any type or item IDs. So all we care about is the U32 scope ID and the U32 type. And then we can do the same thing we always do. If it's bigger than the record size, we bail. Otherwise, we remap type index of func ID, scope ID, and the func ID type. Beautiful. Build info. We have a count, which is a short, and then items IDs. It's a little bit weird because I don't know how the padding works out here. Is there padding or no, is the question. But I assume there's not. So let's say how to do this then. Is the other count also U16? No, it was a long. Or maybe are there multiple build info types? No. Because there were two for the arg list, I might just try U32 for now and then see if that's correct. And it should yell at me if it's wrong, I suppose. Okay, count, and then yeah, arg it says. Sure. Build info is void star record data. Can kind of copy this stuff, and this, all of this actually. Let's just come with me. Say if the build info is too small, we bail. If the count doesn't really work out, we bail. We iterate all of the arguments and remap all of them. Okay. Substring list. This one has a long as a count. Well, it's the exact same thing as arg list. I kind of want to keep these separate because of the some of these are ID records, otherwise other ones aren't. So add node. This is the same code as arg list because it's the same record, but I want to keep types and records set. All right, a little bit annoying. Arg list replace with substr list, substring list. Then not argument type, but substring. Okay. And finally, I don't think we need to do anything about lf string ID. Oh, it does actually have an ID. Okay. So 32 ID to list of substring IDs. Okay, ID, I guess. Void star, or 32 star in this case, I guess. Record data if size of ID is bigger than record size break. Otherwise, we take the ID and remap it. Okay. Count. 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 Would have thought that if I copy and paste that 3 times, I would have to fix it up 3 times. So the IPI type index starts at OX1000, the TPI type index starts at OX1000, and then we compile warnings. So these TPI and IPI headers are not yet initialized. So this is the last thing I think we need to do today, which is initialize all of the data that is in the header. So the way to do this is not to look at this file anymore, but at my documentation. And then we are looking for the TPI header and just read what it tells us. Okay. Sadly, this doesn't have a search function. It's Markdown viewer. If anyone knows a really good Markdown viewer, I would be interested. Okay, TPI stream. The TPI stream, blah, yada, yada, yada. Okay, we have this TPI stream header, and here it tells us about the versions and stuff, about the members. So, TPI stream header. Version is this guy right here. The header size is the size of the header. The minimal type index is OX1000. The one past last type index is what we ended up with. So we just started these up here, and so in the end, after we've iterated through all of them, they should be patched up, should be at the end. So this for the TPI header is the TPI type index at. The byte count of type record data following the header is, can just calculate by first off take the member and say it's where we are currently, so arena current of the TPI stream, and we subtract where we want to start, so following the header, so just U8 star the header plus 1. Okay, are these all the members? Or do I talk about them later? Okay, stream index of hash stream. We are currently not hashing these type indices, so we put that to the invalid type indices, which can be, or which is U16 of -1. So this is U16 -1. And the auxiliary hash stream, which I cannot pronounce that word, is always -1. It's kind of ambiguous if this does even exist or not. Hash key size, number of hash buckets, hash table index buffer offset, hash table index buffer length. We are currently don't have a hash table, so I think I can set all of these to 0 and see what that gives me. That's incomplete. The hash key size is 0. Maybe we have to set that, but probably not. Maybe let's just do. It says the hash key size can be 2 or 4, but in practice is always 4. Okay, I can do that. Okay. And then there's the index offset buffer offset, index offset buffer size. This is also some data structure in the hash stream, which allows us to quickly look up type records by type index. But I think if we just leave out the type, the hash stream, we can also just set both of these to 0 and hopefully it works. If it doesn't, and it really needs these, then I guess we can't test today. And then the UDT order adjust table is something that is purely for incremental linking and is otherwise always 0. So we can safely for now and for ever set this to 0. Okay. And then the IPI stream header looks essentially the same. So I'm just going to actually copy all of it and just say some like the last one past last index. First of all, let's do TPI IPI. I think that should be enough. Yeah, that also didn't screw up anything. All right. What are we complaining about? Stream index of hash stream. Yeah, so this is where my documentation still sort of sucks. Namely, I renamed these at some point, and so they are different in one part than they are in another. So let's actually fix that right now in the documentation. So which one do we like more? Do we like, where are we? Hash stream index and auxiliary hash stream index better? Or do we like stream index of hash stream better? I would say I like stream index of hash stream better. So let's put that in there. And then stream index of auxiliary hash stream. Nope, I can't pronounce that word. It's fine. Hash table index offset. Hash table index buffer offset. Hash value buffer offset. And so I first of all copied these from some other code that was dumping it, the stream header. And then here I was really thinking about it. So I think these names are probably essentially always going to be better. So I'm going to copy this and put it in here. Because, right, these are not the actual hash values, but hash, like the indices are in there and not the hash values for whatever reason. Index offset buffer size. What do I call it here? Index offset buffer. Offset. Wait. Oh, this is length. Yeah, I like length better because it's the same length as offset. Okay. So, let's fix up the markdown. In PDB, readme, most of them I fixed up in the stream table header. So this was called TPI stream header. Right here. And there I now have this one. No, that one I fixed up in the other guy. These values. And then these values. And then the last thing is searching for this one, but with size. Put it to length. Okay. Where were we? it compiles. Right. Now, hopefully, if we run this, nothing breaks. So far, so good. And now I want to check how this file looks. So cv dump of a.pdb. This guy doesn't complain, but it also doesn't print any information for the TPI or the IPI. And that was produced right now. So /pdb/validate. TPI contains more type records than its header specifies. So dumping all of the values, we can see the TPI stream index. The version looks fine, header size is probably fine, minimal type index. One past last type index of the TPI stream is 104. Byte record following the data is 70. These are both -1. Hash key size is 4. Sure, all of these is 0. This looks like exactly what we produced. So that's at least good. And then it says the TPI stream contains more type records than its header specifies. Right, PDB. So why is that? Whenever we produce one of these type records, we are supposed to increment the TPI type index at. And then the TPI stream header is one past last type index is TPI type index at. So let's maybe print whenever this is happening. Writing where are we? This guy. Let's also get the name in there. Okay, maybe don't get the name in there. Oh, I see. Wait. Why is this here? Okay, that was the reason why it said there was more. I pushed another header to the very end of the thing. Are there any complaints now? No. Okay. Then at least my my validation utility thinks it's fine. Let's see what cv-dump thinks about it. It says error on open TPI invalid file format. And yeah. Why? Error on open TPI invalid file format. 11. Well, one of the things we could do, just to see if it's something that we can't fix right now, Microsoft PDB, go into this repository, actually look at the code that produces this invalid file format thing. So this would be in PDB, DBI. We are looking at the TPI stream. So tpi.cpp. And then, well, maybe this would be produced anywhere, but I don't think this is how it works. I think they use error codes. They probably also don't use 11 as an error code. Let's get this to this side. But it says the error is an open TPI, which is probably goes into fopen or something. Validate header. Hash key, hash buckets. Okay, we need to specify the correct amount of hash buckets for the correct size. Is I think what this is saying. Maybe this is the problem. So, number of hash buckets. Do not say anything here about this value, because I'm remembering it to be very specific. It's unfortunate that I'm not talking about it here. Okay, this is the hash function. If you're not going to do today, yeah. It's also not what I care today about right now. Where could I look this up? Well, in my compiler, I guess it has like a pretty ancient PDB implementation. So let's look at that. Here in Conf Writer, wherever we are. Ugh. I hate this file with a passion, so no one look, please. But here's something similar to the stream index stuff. Actually, the validation utility also should have it. Do we still have that? No. Validate.c. TPI. Okay. Yeah, I don't get into this branch, so I don't validate these values, which maybe is wrong. Number of hash buckets. Has to be between OX 1000 and OX 40,000. Okay. So I'm going to note somewhere in Scratch for now. Make sure that the documentation talks about limits on the hash table count. Anyway, that aside, we can now go into here, into the not conf writer, into write PDB, and say that the number of hash buckets OX 1000, and then see if that does anything. Well, it did do something. It crashed cvdump. So we're not quite there yet, I suppose. One thing I could also test, if that was actually the problem, is to go into write PDB and leave these as 0 and see if that does anything. Yes, it tells me invalid file format again. So one thing that could be it is this build info thing that we talked about, where maybe this needs to be a U16. So let's try that. If it's not this, I think no, it's not. I think that means I'm gonna call it here though. I'm gonna investigate off record why this is crashing, what is wrong with it. It's probably that one of these type records that we are producing is wrong in some way. And cvdump is apparently not checking that correctly. And yeah. Because my utilities again think it's fine. I could try remedy and see if that crashes. A.exe. It says symbols out of sync. And well, there are no symbols and no named types. So I can't actually do anything here. Can't let it show me any types. But yeah, okay. So that was it for today. A little bit anticlimactic because CV dump crashes and well, anyway, I hope if you still enjoyed it, thank you for watching. Maybe see you next time.